Okay, thank you very much, and thanks for the organizer for this very nice conference. So I'm going to talk about the oscillatory currents, specifically how they fluctuate, and I spent quite some time on why should you care. So I'll devote a large portion of my talk to the motivation, and this is a work that was done with Bertrand, who is here. So okay, so you already see here that's an ion trap, and this would play an important role in the motivation. The specific motivation for our for the question we are asking is what's called anomalous heating in trapped ions. So why trapped ions? So trapped ions are very, very useful experimental setup in physics in general. They are one of the potential candidates for scalable quantum computers, but even in my point, even more important is that they are really good for many physical problems. For example, the most accurate atomic clocks are actually trapped ions. At the moment, it's aluminum ions. And they are very useful. You know, they study many body physics with them, fundamental quantum effects, and even they get a precision measurement. For recently, they measured the the magnetic dipole interaction between ions, and they were able to rule out some high energy theory. So this is really a useful setup in physics in general. And let me give you the 101 on this setup, what you need to know at least for this talk. So you all know that if you have a potential which is satisfies the Laplace equation, then it cannot have a minimum, right? If you have a minimum, you expect something like that where A, B, and C are positive, but since it satisfies the Laplace equation, you cannot have all of them positive. So at least in one direction, it cannot be trapping. And the solution is a well-known pizza that you probably... Right? So you have the Matthew equation, that's the simplest case, where A might be negative, so this would be anti-trapping, but with strong enough temporal fluctuation, you can stabilize it, and that's the effective potential that you get, right? So that's you all know. And that's how they trap ions. They use, there are many, many different configurations where they apply periodic driving, so they apply RF fields on these traps, and they are able to trap the single ion somewhere, depending on the configuration. Recently, they were able to generate a flat. Mm-hmm. Right. That's it. The Kapitza and the parametric resonance.
Kapitza is not a resonance.
Okay. Anyways, so importantly now, they can generate such traps which are flat. This will play some important role. So this is the basic apparatus. It's quite old. It's called the Paul trap, and it's old. What's less old is Coulomb's ion. It doesn't really matter the exact laser cooling, but the basic idea is that you have thermal currents on the electrode. They, of course, generate electric fields that fluctuate and heat up the ion. But you also have some dampings that you move the ion, you have a charge image that, right, mirror image that would move and go through the resistor, so you have damping. And of course, that the temperature is just the balance. The temperature of the ion is the balance between fluctuation and dissipation. And the main point is that with laser cooling, you can really increase the damping by a huge factor, lowering the effective temperature to something very, very small, right? So whenever the lasers are open, you have, sorry. Where was I? So whenever the lasers are open, the temperature is really, really, really low, right? And, but for most of the experiments, you don't see them, but yes, they are, yes, so through, no, the lasers are not trapping. The trapping is the RF field. The lasers are just cooling. Okay? Okay, this is the wrong direction, right? But for many of so whenever you want to use your trapped ions, you have to close the cooling lasers. So, for example, if you build a clock and at some point you want to read up what time it is, right? You have to close the trapping laser, the cooling laser. Same if you want to do quantum operations. And of course, when you turn the cooling laser off, the ion heats up, right? You take it at a distribution which corresponds to, I don't know, some millikelvins, and suddenly it's room temperature, right? Of course, the rate at which it hits limits the off time, the number of gates in quantum computer. It's also a kind of limits the accuracy of the clock. And the surprising thing is that if you do some naive estimation, you assume that thermal noise is what should hit your ions, right? Then in measurement, in typical measurement, you find something which is roughly 3 orders of magnitude higher rate than the calculations that experimentalists usually do, right? So this is an example where they measure it as a function of distance. Maybe I'll explain in a moment why. But this is not a single, so we have this 10 to the 3, roughly, it's not exactly 10 to the 3, but it's a faster heating rate, higher than expected. This was measured for over 20 years, more than 100 traps around the world, different electronics, frequency, material, ions, whatever. Right? There was a 2015, they wrote a review of modern physics. They surveyed 66 different traps where this phenomena was exactly measured. And since then, there were many other measurements. So it seems to be all around. It's a 3 order of magnitude effect, and we don't understand. And let me tone down. I'm not going to solve this problem, okay? But I think this problem might have a solution that is related to what we do here, and it poses an interesting setup to study. Okay? What? Probably not, because the laser cooling essentially is the initial condition. The question is what happens when you stop the lasers, right? You start, for all practical purposes, at 0 temperature, right? This millikelvin doesn't really matter much. You stop, and then you look at the heating rate. So there is no laser during the heating stage. Okay? And of course, they try. Okay, good question. In a moment, I'll go through. So they considered many type of noise, strange noise. That's why, for example, they measure the distance between the ion and the electrode because they think it's like a patch potential on the electrode and many things. None of these surveyed, none of these explained. Okay, so they really went through all noise that you can, or most noise that you would guess, and they are all far off, right? Since it's an old problem, and these days they build traps to measure the anomalous heating and try to explore it. There are many things that are known about. So roughly all of them is 10 to the 3. Of course, it's there's no, this is roughly 3 orders of magnitude. The surface cleaning reduced the heating rate. So this is attained after they've cleaned the surface very carefully. If you don't clean, you have higher noise, right? So that's why they look on pinch potential and etc. Temperature changes the heating rate. So they build crazy traps that they dive into, liquid helium and all kind of such things to measure the temperature dependent, and temperature plays a role here. So there is a temperature dependent. However, scaling with trap frequency and scaling with ion electron distance, they don't agree on these. So that's, for example, if you assume that the heating rate, they measure the heating rate by the average, they assume a harmonic oscillator for the trap, and that's the energy level and the rate of change of the average energy level. If you assume it's case like omega to some power, as you can see, different measurements, it goes from 6 to -1. So this doesn't seem to have anything very that you can count on. Several traps with varying distance were built. This is very difficult experimentally to build a setup where you can change the distance between the ion and the electrodes. But since they believed originally that this is patch potential, they wanted to measure the scaling. And these are from 2001. The first measurement was that one. And since then, there were quite some few. If you assume distance, scale exponential with distance, you see that it ranges from d to the -4 to d to the -2.5. Doesn't seem like anything specific. So, it's not obvious what is the mechanism, and of course, yes. Mm-hmm. Yes, it's definitely depend on and this is why it's so, for example, difficult if you change the distance between the electrode, you have to change all the resonance and all the frequency. Yeah, that's what I said. It's difficult experiment to build such a trap. The flat trap are kind of easier. They can manipulate the shape of the effective potential, but still, it's not an easy experiment, and they have to then, change all the circuit based on that. Yes. Mm-hmm. Yes. Yes. So we have been playing with this for quite some time. So when you think of, okay, you go over what the experimentalists are calculating. So they always use this effective potential rather than the periodically driven system. And you can ask, okay, what's the heating rate? What's the ratio of the heating rate in this system and that system? So for A and Q, Q is right for A and Q that are relevant for the trapping. So that's where you have no trapping. And of course, at the edge of the trapping zone, you wouldn't be surprised that there is a huge difference. But of course, experimentally, they work where there is at most a factor of 2 between these two calculations. So that's the first naive thing that's the first thing you would check. But this is not a significant effect. Next thing is, as David pointed out, when they measure the heating rates, they actually assume a Boltzmann distribution. That if it is a Boltzmann distribution, you can measure the n dot based on the based on measuring the difference at n+1 and n-1. So many kind of assumptions are into this calculation. And of course, during the relaxation, it's not a Boltzmann distribution. So once you stop it, it's not, you stop the laser, it heats up, and it's not in a Boltzmann distribution. But you find out that, okay, this is only 1.2, and it's in the wrong direction. So this is actually, if you do this careful calculation, you find that assuming a Boltzmann distribution would give you somehow higher than expected. So that's, again, not a... And we tried a few other things. But after trying a few things, you understand that, as Jorge immediately said, that the fluctuation must be stronger than the thermal noise. So assuming a thermal noise, no matter how you drive the system or whatever, this is not going to work. You're not going to have 3 orders of magnitude. And then you think, okay, what can generate that? Of course, you are driving the system with the external field to trap the system, right? So you have these strong currents that are flowing through the electrodes and are responsible for the trapping. This might somehow enable you to generate a strong fluctuation, right? And moreover, so you have this oscillator currents, and you care not about the DC effect, but on the fluctuation in the relevant frequency. So only fluctuation at the trap frequency are the ones that would that would generate heating, right? So this suggests to look at current fluctuations, and the current fluctuation in periodically driven system were studied. Rafael Chitrit is here in all these works. So they were already studied, but all of these works, they look at the DC part of the current. So they look at fluctuation in the DC part of the current, and this is not the part that will heat up your ion. What would heat up your ion is, of course, the frequency at which the ion is trapped, right? So, so that kind of naturally at least posed the question, okay, how do you calculate the current fluctuation in periodically driven system, but not at what we usually calculate, which is the DC current at some other frequency, right? So you look at this right? This would be the empirical current. You just weight it at the current, so with the cosine, say, right? And how you can calculate the distribution of the current, well, there are experts here that can explain much better than me, but you build a tilted operator from the corresponding Markovian operator, and you look at the largest, so the large deviation form can be calculating from the largest eigenvalue of this tilted operator. But now this tilted operator, since you are periodically driving the system, you have the omega drive that corresponds to the currents, but you care about difference frequency. So this operator has 2 frequencies in it, right? So whenever one of them is 0, it's very easy. This is what, it's not very easy, but this is what was studied already. You have periodicity in the operator, and you can do Fluctuation operator. So you integrate it over a cycle and look at the largest eigenvalue of this Fluctuation operator, and you can calculate from it the generating function from which you can extract the large deviation. The large deviation as usual. So nothing happens. So as long as one of these frequencies is 0, then it's periodic and everything is okay. And of course, for commensurate ratio, Fluctuation still holds. So the cycle time would be the commensurate time corresponding to 2 frequencies. But immediately you ask yourself, okay, in the experiment, these are 2 random frequencies. They are not, not necessarily commensurate. And then the Fluctuation operator is non-periodic. You cannot use Fluctuation. So what do you do in this case? it turns out that the first thing is you ask, okay, is it well defined, and can you actually do something with it? So Oselade's theorem, he looked on a very similar problem in the context of Lyapunov exponents of systems, and you can use his results. If you look at this as a function of time, or you just integrate this as a function of time, then this object, which is exactly what we want, exists. Okay, so it's well defined, and you can use it in principle to calculate the large deviation function. So someone did the hard work previously, some smart mathematicians, and of course everything in principle should work. And how to calculate it? So that's definitely not how we are going to do it in practice, but to show you the problem, let's discuss two options of how would you naively calculate that. So suppose you can calculate it for every time, then you would take this limit, right, suggested by the Oselade's theorem. Or alternatively, we said that we have for any rational we can use Fluquet. So let's take a sequence of rational that converge to your non-rational ratio and use Fluquet, right? So if everything is fine, these two should agree, right? If this is a continuous function of the ratio, then these two should agree. But of course, they are not. So this is not a continuous function of the ratio of the two, which is kind of the interesting part that I want to explain next. So again, this is not how we calculate it, but that's kind of an explanation that you find after you understand that this is not a continuous function. So the dependence, you have a Fluquet, you have a periodic operator with two frequencies, but you of course depends only on omega t. So either this omega t or that omega t, right? And it's periodic in either this or that, but not in both of them. And you build this M operator, this integrated operator, by kind of integrating L along a line. But it's an integration over the torus, because if you repeat in both, right, you have the cycle time for the current, the cycle time to the drive, and you only care about where you are in the torus and not about how many times you wrap it, right? So that's your torus. And if the ratio is incommensurate, then you do a line integral over something that kind of wraps ergodically over the torus and never goes back to the same point. So it covers the torus. A commensurate ratio, you get a closed line, of course, right? You cycle the torus and go back over a line. So not surprisingly, whenever you hit a commensurate ratio, you close the line, and it doesn't look like an integration over the torus, so you get a discontinuity. Whenever you are a continuous integration, the continuous integration is whenever you are non-commensurate, you wrap around the torus forever, and this is a continuous. This would be a continuous contribution. That's again. This is how you calculate the fluctuations in the current, and strong fluctuation in the current would generate higher heating rate for the ions, right? But I'm not saying that this solves the problem. None of our calculations, so this is a nice result, but it didn't give us real magnitude in the heating. This is still open. Yes. So you, right? You have currents in that are, but you don't generate this current deterministically, right? You have currents by driving the system, and so the currents might fluctuate. So they don't might, they definitely fluctuate, right? But we care about not the usual integrated current. We care about the integrated current at a given frequency, which is different than the driving frequency. Yes, yes, like the fluctuation, the coefficient of the. Yes. So the heating probably cares mostly about the second moment, right? About the fluctuations. But why not calculating all of them? Fourier transform, right? So if you have fluctuation in the current, you'll have fluctuation in the electric field, which would hit the, generate heating for the ion. The currents are what holding the ion at the end of the day, right? They are generating electric fields at the ion fields and hold it in place. If you have fluctuation, okay, it's non-deterministic. This would cause some uncertainty in the position. Yes, it is. This will at the end of the day. This would generate a noise. If you had no fluctuations at all, the ion would will be sitting there without any heating, right? You need some fluctuation in something to generate heating for the ion. Otherwise, it would stuck there. Right. But without heating. I don't think so. It's a single ion at the end of the day. You look at the distribution and you associate. In this sense, of course, yes. But it's not a macroscopic system. Okay, so you let me go back to that. So in incommensurate ratio, you kind of integrate forever over all this surface, whereas the commensurate ratio, you just go over a line. And of course, this would be continuous for the irrational, but not for the rational, which is just like the Matthias functions that you probably learned in the undergrad calculus, which is a continuous function on the irrational and non-continuous on the rational. And if you have something which look like m over n, then n, and m and n are non, right? They don't have a common factor. Then n dictates the jump. Why? Because the larger n, the closer you will be to this integrating over. The more cycles you'll do here, and you'll be closer to integrating over the area. What you cannot do is you cannot really. So this is kind of think of it as a caricature, because these L's are not. They are not commuting between themselves at different times, so this is not really, you cannot really do the ergodic average, right? So that's kind of the picture of why you have such a very strange, cumulant generating function in this as function of the frequencies. How can you calculate? So Bertrand came with a very nice method to do this for simply connected manifold. And the basic idea is not to look at the current, but rather to look at position. And for simply connected manifold, you can actually go from the statistics of the position to the statistic of the currents. There is no tilting in this case, and so you have only one frequency, and you calculate the cumulants one by one, and these are not easy calculations, but they can be done. A simple example is the first example is a underdamped Ornstein-Uhlenbeck process, where you know everything is going to be Gaussian, right? In advance, because it's a linear system. You choose some periodic driving for your, say, diffusion, and you only have the two moments, so this is going to be discontinuous only at these, and you can actually do it also for finite time, and that's the result. You see kind of the peaks. Maybe a different option is to use something like a discrete state system. You can repeat basically everything for a discrete state system, and there is this nice dynamical invariant method that was recently suggested by Takahashi in this paper, where you can actually do the calculation for all the cumulant generating functions, all order. And then what you have is that for the irrational number, you have this continuous function here. And for the rational, you have these jumps that, right, you see that at, say, 2 or 1, you have big jumps. And for small rational with small n, you have kind of much smaller jumps. So this is somewhat funny observable for this type of system. So if you have two periods, then the cumulant generator function become an interesting object. This is we choose the tilting to be, say, 3, and we calculate it for a fixed driving frequency as function of the current frequency. The moment generating function at mu equals 3. Okay. So the current fluctuation considered so far, right? You have very strange behavior, but you don't get 3 order of magnitudes for the fluctuations. But there are additional experimental evidence that might help and at least suggest other calculations that we might be able to do. So, for example, in this measurement, they measure the effect of treatment. So I told you have to carefully clean the surface, and this change the heating rate, right? So then you think of it, you say this is the current that they are driving is at a megahertz rate, and at these frequencies the current only flows on the surface. There is this skin effect where all the currents are at the surface, and cleaning the surface is important. And another nice experiment that actually they didn't plan to do, but at some point they tried to measure the heating rate as a function of the distance, and now they have these flat traps, so they can put an electrode externally coming from the outside, which is not part of the trap, and when it was not grounded, it generated no heating. So you have this flat, and the ion is stuck here. So you can come from, with a different electrode that is not connected to your circuit, and look at the heating as function of the distance. And when this electrode is not grounded, so when there are no current flowing, it's not generating any heating. So it definitely suggests that the currents are responsible for the heating. And what we didn't check is current fluctuation when there are, when you have, so you can imagine that since cleaning is important, so that the surface on which you are driving, so the potential of the potential along the surface might be very important. That's kind of a natural thing to look. Again, I don't know if this would explain the 3 orders of magnitude. At the end of the day, we don't know what it is and whether it is really coming from something here. Maybe they all buy the same, chip from I don't know where, and it's completely unrelated. But this definitely suggests an interesting calculation to do. With that, let me thanks, of course, first Bertrand, my funding, and you for listening.